Hey, physics class. So it's the last week of the school year coming up, and with that being the case, it seems like it might be a nice time to try something a little different, a little unusual, maybe even a little fun, just so that we can, put a nice bow on the end of a very unusual year. So just to take a break from the, hard and like, gonna get me kind of stuff, let's just do something a little more of a diversion. And what subject do physics students or just science students in general like more than space? So I'm going to take something from the first semester, something we did recently, and kind of combine them together to make something about space. So let me remind you of Coulomb's law, which we were doing a couple weeks ago, in which force is equal to a constant times two charges, the product of those charges, over the square of a distance separating them. This right here is a good example of what is called an inverse square law. And an inverse square law is just a natural consequence of living in a three-dimensional universe in which energy spreads out, and the square comes from the imaginary surface area of an increasingly large sphere in which the energy is spreading. So that basic form is going to describe any force which extends through space as a spread of energy. And that's the second semester tie-in. The first semester tie-in is actually just regular old gravity. We did a lot with gravity, but we did gravity like this. We did weight is equal to mg. That would just be F equals ma, except we put g in for a because the acceleration is due to gravity. We also had things like potential energy and its counterpart being kinetic energy. Those are all equations that we would have had, on our midterm. However, we do have an inverse square law for gravity, and we didn't do all that much with it. I think we did some, just not that much. So let's go ahead and get that. We have to have a force, and the constant is going to be a uppercase G. Then instead of two charges, it will be two masses, because this is a force due to mass, that's gravity, instead of a force due to charge. And once again, divided by the distance squared. Okay, so that being the case, let's get the constants straight. So when we were doing Coulomb's law, of course, we had to look up a value for K. And I'm going to go ahead and just look up a value for G. So this is going to be Newton's law of gravity, big G. And the gravitational constant, according to this reputable website, is 6.67, that's enough decimal places, times 10 to the negative 11th. So I'm going to go ahead and write that in. 6.67 times 10 to the negative 11th. So we've got a value for G. Now, since we're going to be doing some math with this equation, we're going to need two masses, and the two most obvious masses we can do are the Earth and, well, I guess me. As always, you can use your own mass if you'd like. I just, don't like to volunteer other people's masses for problems. So, mass of the Earth in kilograms. It's a lot. So let's go ahead with that. The mass of the Earth is 5.972 times 10 to the 24th kilograms. Okay, and just for the sake of making the math slightly easy, we can say that the mass of, I'm going to go mh, because if I wrote me for Estes, it would be confusing. This would be h for human. Mass of human, I'm going to go with 75 kilograms as an approximate mass for myself. I don't even remember the conversion, but you know, the math is easier. Okay, so given this, we should be able to confirm that gravitational acceleration on the surface of the Earth is 9.8. Oh, but that means we need one more piece of information. That's going to be the radius of the Earth in meters. Radius of the Earth in meters. 6.371 million. So that's the last little piece of info that we need. The radius of the Earth equals 6.371 million. 6.371 times 10 to the 6 meters. Okay, all that information is what we're going to need to first confirm that gravitational acceleration on the surface of the Earth is 9.8. And then 2, we're going to go into space with this. So I'm going to put this paper to the side. You're going to want to have these numbers on hand to work with. And then we'll see where it goes from there. So paper number 2. All right, so starting with this equation at the top, got my calculator ready. Okay. Force equals big G m1 m2 over r squared. So for me on the surface of the Earth, that is going to be G G times mass 1 would be mass of the Earth, 5.972 times 10 to the 24th. That's the mass of the Earth times Alright, just making sure everything still works. Where am I now? Yes. That's the mass of the Earth. Now I need the mass of me. 75. And now the radius squared. That would be 6.371 times 10 to the 6 squared. Okay. Well, this is going to be quite a calculator trip, but it's not beyond us. We can do this. So let's get it done. Okay. Oops. I already made a mistake. 6.67 times 10 to the power, let's see, negative 11. Okay, that's going to be times, oh boy, 5.972 times 10 to the power 24. That is huge. Times 75. Still huge. Divided by And now I need parentheses for this. 6.371 times 10 to the power 6, close parentheses, squared. 736, almost exactly. What does this represent? Well, this is an F, right? So F equals 736 newtons. Okay. Well, newtons is the unit of force. So that means we are comparing this to F equals ma. So the question is, if we had just done ma, or in the case of the actual equation for weight, mg, is it the case that this is my 75 kilograms times the 9.8 meters per second squared of gravity? Let's see, within a rounding error, of course. So 75 times 9.8, 735. Absolutely incredible. That is a difference of 1 out of 730 something. That is, wow. Okay, so that's about right. Okay, so if we were to do a little bit of simplification here, we might notice that my mass in this expression is just my mass in that expression, which means that all of this acceleration is just the rest of it. Or, if I could write this one more time, the acceleration due to gravity, I could just write a lowercase g, is equal to Newton's gravitational constant, big G, times the mass of the planet divided by the square of the distance. Now, that is a lot simpler, isn't it? But what's interesting is that also means that we can use that expression, big G m over r squared, in an equation where a little g was required. Now, back on the first page, we had a couple equations that had a g in it. For example, this one, which we just used, but also that one. So, if you were inclined, you could rewrite this physics equation, E equals mgh, as E equals g m1 m2 over r squared h. Now wait a second, what does h represent? Doesn't h represent a distance from the ground? Well, that's kind of what r squared is. So you could, again, rephrase h as an r, or I should say, h would be r minus the radius of the Earth, since we're standing on its surface. But we're going to just go ahead and leave it like that for now, because we don't want to get too far ahead of ourselves. This was the point of this sheet of paper. So that's what we're going to go ahead with. We want to get into space. That's the goal here. So How high can you jump? Can you jump 6 inches off the ground? 12 inches off the ground? And I'm not talking about like if you tuck your legs up. I mean just like, what's your vertical? Just how far off the ground can you get? I don't think you could get into space. I mean, I can't, so I just figure probably nobody can. But what would it take to jump into space? I actually want to show you how that gets calculated. It gets calculated like this. Okay, so if you were to take this equation, E equals mgh, and basically ask the question, so I have a mass of 75 kilograms, and we're on the Earth, so g is equal to 9.8. Let's say I was able to jump up a height of 1 foot, just 12 inches. Let me get that in meters real quick. That would be, that's 0.3048. I just one I remember. So let me get a height of 0.3048 meters. Okay. How much energy does it take for me to do that jump? It's a very basic calculation. All you need to do is plug these three into this equation, and that'll be oops, 75 m times 9.8 g times h, 0.3048. All right, that's how much energy it would take. The amount of energy it takes is 224 joules. All right, so what does that mean? It means that when my muscles burn energy in order to perform that jump, they burn that much of it. And that's assuming they're perfectly efficient, so they actually probably burn a lot more than that. But that is the energy cost of moving that much mass that high. Okay, so let's start getting fictional here. How much energy would it take for me to jump up a kilometer? Okay, well, this is going to be a little ludicrous, but let's go ahead and do the math anyway. To jump up a kilometer, we're talking same mass, same gravity, but now the height is 1,000. Okay, so we just have to do mgh here. M, that's 75, times g, that's 9.8, times h, 1,000. Okay, 735,000 joules. Right. Now hold on just a second. It's still me, so 75 should stay 75. And I just made up 1,000, but should I be using 9.8 here? See, 9.8 is the acceleration due to gravity, but on the surface. If you're all the way up at a kilometer, is gravitational acceleration still 1,000? I'm sorry, is gravitational acceleration still 9.8? Okay, probably, but let's get up a little higher just to make sure that we'll get a different answer. Let's do this at one more height. We'll do it at 1,000,000. Do 1,000 kilometers up. So mass 75. Gravity is let's leave that one blank for a second. height is 1,000,000. What will we use for gravity? Referring back to this is what we're going to use for gravity. Gravity is going to be g m over r squared. Big G m over r squared. Okay. This is where it's going to get just a little crazy. So if I want to jump up 1,000,000 meters, but gravity at the top of that is going to be weaker than gravity at the bottom of it, what I'm going to do is I'm going to break this down into 10 smaller jumps. Obviously, if you were to make one jump, you can't just like stop in midair and jump again. You know, it's not like some sort of real life video game double jump. However, the physics are going to work out the same in terms of the energy cost, so you'll just have to go with me on this one. So this is the equation that is going to start our next page. Just get the paper separated. All right, so scrolling down. All right. Our jump is going to be 10 individual segments of 100,000 meters. Those of you who have taken calculus, you're like, oh, okay, I know what's going on here. Or at least you will in a second. So let's go ahead and have the ground here. This would be height equals 0, though it would be r equals 6.371 times 10 to the 6. See, we're 6,371,000 meters from the core, though we are at a height of 0. Okay, so if I have a height total jump that I'm looking for of 1,000,000 meters, then I've got to break this into 10 steps. Let me see if I can get this without messing it up. On a whiteboard, I could just erase it if I get it wrong. I have to get it right. So there's 5. 1, 2, 3, 4. 1, 2, 3, 4. Hey, that's not bad. That's not bad. Okay, so each of these is 100,000 meters. 100,000 times 10 is 1,000,000, which means I have 10 different distances from the core of the Earth. I have 6.371 times 10 to the 6. 6.471 times 10 to the 6. 6.571 times 10 to the 6. 6.671 times 10 to the 6. Do you see that? I have to add 100,000 meters every single step. So that's just that first decimal in the expression in scientific notation. So just a couple more steps to go. I really want to avoid making a mistake because I was talking and writing at the same time, but nothing is quite so entertaining as just watching a dude write stuff down. Am I right? So here's our last one. We end up at a distance of 7.371 times 10 to the 6. It went up a whole million. Okay. Well, since there's going to be 10 different heights, there's going to be 10 different values for R. Now, I could do all these on a calculator, and that would be lots of fun to watch, now wouldn't it? No, instead what I'm going to do is I'm going to just do this in a spreadsheet because it's going to go a lot faster, and who knows, you might even learn a little something about Google Sheets. I don't know. Okay, so I've got 10 different heights starting at, I'm going to do them vertically in the right order. So I've got 7,371,000 here. This is going to be equal to that minus 100,000. And I'm just going to copy this all the way down. There we go. So that's at the ground. All right. Righty. So these are all the different distances. Now, from the core of the Earth. Now, with that said, we're going with that version of gravity, right? We're going with this G. So I can actually calculate here. Let me put, so this is the R. This is going to be the G. This is equal to 6.67 times 10 to the negative 11th. That's capital G. Times M. That would be the mass of the Earth. Not me. Mass of the Earth. Let's see. Mass of the Earth was that huge number. 5.972 times 10 to the 24th. Yeah. All right. So I've got my capital G, little m, and now over r squared. Over, this is the fun part, r squared. Okay, is it going to be 9.8? No, it's way less than 9.8. It's only 7.3. Up at that height, that's what gravity is. But as we go down, you see it increasing until down on the ground, it's 9.8. Do you see that? This one right there, that's the 9.8 when r is just the radius of the Earth. When you're on the surface of the Earth, you get a gravity of 9.8. There's too many decimal places here. Let me see if I can... There we go. That's a bit more like it, isn't it? All right, so let's tidy this up. Lovely. So, on the ground, gravity's 9.8. Up at a million, it's 7.33, which means you can approximate this as jumping from a height of 0 just to a height of 100,000 meters. Just going a tenth of the way, you can do your own little E equals mgh just for that one. And then do it again for here. So let's do that. This is going to be the energy for the jump. All right. So to get up to this height, you know what? Yeah, okay. To get up to this height, you would have to move 75 kilograms up against 9.51. Okay, no. I need to start down at the ground. In order to get up to this height, yeah, you need to move 75 kilograms against a gravity of 9.8. So this is going to be mgh, where it's m is 75, g, sorry, I should do times, g, which is that, and then h, which is just 100,000.
All right, so that's the energy it takes to jump the first 100,000 meters. The energy it will take to jump the next 100,000 meters will be less, because instead of jumping with a gravity of 9.81, I jumped with a gravity of 9.51. I can just copy this up, and there I have it. The first 100,000 meters cost me this much energy. The second 100,000 meters cost me that much energy. The next 100,000 meters cost me that much energy. Do you see every time I go up, the energy cost is less because I'm jumping against a weaker gravity? Well, if I want to know the total energy, I just need to add it up. So I guess I'll do that. Equals the sum of those. And it's a lot. It's 645,545,815.6 joules. It's a lot. Okay. Now, I know not all of you have taken calculus. However, you all have taken pre-calculus. Now, I want you to look at the form of this formula. Okay? I am multiplying two constants, 75 and 100,000, by that column. This column has a square in its denominator. Now I ask you, if you are adding up a sequence which has a constant, that would be the 75 and the 100,000 and the 6.67 times 10 to the negative 11th, the mass of the Earth, all of those are constants. And a square in the denominator, does this series diverge? No, this series converges, which means these values are decreasing in such a way that taken to infinity, they have a limit. Which means there is some energy which can get me off the planet, never to return, never to fall back down. I want to find out what that is. So here's what I'm going to do. I'm going to start it, and I'm not going to finish it. I'm going to let you finish it. So I need to reverse the direction on this. So I'm going to start a new sheet. This is going to be my R. This is going to be my G. This is going to be my E. And I'm going to have a running total of E, I guess right here. All right, so here's how this is going to go. This is going to start on the surface of the Earth, and I'm going to go in 100,000 meter increments, which means the next height is going to be that plus 100,000. Gravity is going to be equal to, following this equation, 6.67 times 10 to the negative 11. That's big G, times mass of the Earth, 5.972 times 10 to the 24th, divided by this squared. See, 9.8, just like it should be. Let me neaten some things up here. Don't need to take up all this room. Okay. There we are. Yep, everything's going just as it should. Okay, so I'm not going to have any energy staying on the ground. So the energy at this height is going to be equal to m g, that would be that one, h. Okay. So the h is going to be 100,000. Okay, now a word. Why am I using this gravity instead of that one? It's because that was the gravity when I jumped. That's all. Okay, I do want to make a slight amendment here. Oops. I don't know what I just did. I want to make a slight amendment here. I do want to make this a bit more flexible. I don't want to force this to be me, and I don't want it to have to be 100,000 meter jumps. So here's what I'm going to do. I'm going to I'm going to give myself a little space where I can set what m is equal to, and I can set a change in height. So right now I'm 75 kilograms, and right now I'm doing 100,000 between. So I'm just gonna make a little note here. This isn't going to be plus any old thing. It's going to be plus that number, just whatever this is. And similarly, this 75, yeah, I really want that just to be whatever number happens to be here. So that'll be E2. Oh, right, and I need this to stay whatever that is. Okay, there we go. See, now if I lose a little weight, everything, straightens out. And if I don't quite jump up so high, then that gets straightened out too. Anyway, oh yes, and of course equals that plus the previous, which happens to be nothing right now. Okay, well, it's copy paste time. Whoo boy. All right, so this is it's getting a little hard to look at. All right, so whole numbers, right? That's nice. All right, so this is still getting a little nuts. You know what? Actually, I think it might actually be time to speed this up. All right, 50. All right. Here's the good stuff. I'm going to graph this. If I can find where the graph is. I have this shrunk down so small. Oh no. Oh, there we go. Okay, I want a scatter. Line might do, but I really want scatter. Oh, fine. Okay, look at that. Do you see it bending down? See that? It's bending down. Okay. Out of my way. We got to go further. We're going to go down pretty far. Come on, come on, come on, come on. See, this is one thing that's great about spreadsheets. All right, I'm going to go down to 500. All right, at 500, I want to see how far we've jumped. Okay, so this time we have jumped 100,000 meters 500 times. What is that? Oh, hold on. can't do that math in my head. 100,000 times 500. What? Holy cow, we went up 50 million. Okay, so that's like 10 Earth radii. So we're basically 5 Earths away. At this point, gravitational acceleration is only 0.13. Now, do you notice how long it takes gravitational acceleration to change at this altitude? Do you notice how the amount of energy it takes to actually perform those jumps is so much less than it used to be? Do you notice how slowly this is changing now? Let's graph this, shall we? Look. Look, it's evening off. You know what this means? It means that if we continued this, it should actually like reach its limit, and we could calculate the total energy it takes to get 75 kilograms off the Earth permanently. Well, I mean, oh, that's sheet 1. What's the holdup? Let's get it. Spreadsheet's going to do all the work. So I just gotta let it go. Should I stop at 1,000? Oh, it wanted me to. All right, so 1,000 it is. All right, let's graph this thing. Oh no, I can't. Oh no, it's not letting me graph. Apparently, having Google Sheets this small is a problem. There we go. There it is. All right, it's looking like it's leveling off right around there. Okay, somewhere between. It's a lot of zeros. Oh my gosh, it's so small I can't read it. 0, 0, 0, 0, 0, 0. 4.5 trillion joules. Oh my gosh. Somewhere around 4.5 trillion joules. Okay. So, could be wrong here, but it looks like to get 75 kilograms to escape the Earth, and that means give it so much energy that it will never fall back down because it has enough energy to reach any height. It's going to need 4.5 times 10 to the 12th joules. There was another equation for energy. This one. There is some speed that can give me that much energy. Well, let's solve for it. What kind of speed can do that? If we are taking that equation, E equals half mv squared, and we're solving that for 4.5 times 10 to the 12th joules. Okay, I know half, obviously that's a constant. M is 75. Velocity is the only unknown, equals 4.5 times 10 to the 12th. Well, so what we have to do is divide both sides by half of 75 and then take the square root. So V is going to equal the square root of 4.5 trillion over half of 75, which is 37.5. Well, let's see what it is. Okay. Square root of 4.5 times 10 to the 12. I'm so excited. Divided by 37.5. Wow. 346,410 meters per second. If you could start me off at that speed upward, I will never fall back down. That is what is called an escape velocity. 346,410 meters per second. Why will I never fall back down? Well, there's two ways to answer. One is, if I have a velocity of that magnitude, my kinetic energy will be 4.5 trillion joules. And that is equal to the total amount of gravitational energy that the Earth has on me. So give me enough energy and I can just break free. The other explanation, though, is if you start out with this much speed, at every single one of these altitudes you reach, you will decelerate a little bit. However, at every new altitude you reach, your deceleration is a little bit smaller. And because it behaves according to the reciprocal of the square, it ends up being a series that converges. And that means there is a finite amount of deceleration as long as your velocity is this high. You will never be fully decelerated, and thus you will never fall back down to Earth. That is called an escape velocity. Holy cow. So, obviously, going that fast would kill me. But it is a possible speed. I mean, there is a speed limit to the universe, and that's not even close. The speed limit of the universe is about 100 times that. I'd only be going about 1% the speed of light. Could you have a planet so heavy that its escape velocity was the speed of light? It would be a very dark object. What might you call such a thing? Well, anyway, I've just been doing math for like most of an hour. So where are we going to come in here? So what I'm going to do is I'm going to simplify this for you a lot. To just come up with an equation for an escape velocity would require us to do a little bit of calculus, or we could just look it up. So let's look that up. Formula for escape velocity. And there it is. 2 gm over r is square root